Okay.
Okay, so may I proceed or should I wait?
Does anybody else that is checking on the accounts have an opinion on that? Because worst case scenario, we just record it and put it afterwards as we did with the other material.
Yeah, it's also an option.
Yes, let's continue. And then, so Paola, you can introduce Jocelyn Bell for our audience. And then I think the other option will be we will record and then put it on YouTube after it.
Okay, great. So let's get started. Welcome to this special talk of this second edition of As Astrocientistas. And as you all know, we have been meeting during this week together women that work in astrophysics, cosmology, and gravity that are Brazilian or with some ties to our Brazilian community. And in the last edition of this meeting, we have decided to invite a person outside our community that nevertheless inspires us a lot. So in the last edition, we had a talk by Andrea Gies, which was wonderful. And then we started with very high standards. But fortunately for us, there are other women that have made groundbreaking discoveries in science. And one of them is Jocelyn Burnell. So for this second edition, we have Jocelyn, who has discovered pulsars when she was a graduate student in radio astronomy in Cambridge. And she opened up a whole new branch of astrophysics. And now she's a visiting research fellow at Oxford and chancellor of the University of Dundee. She was president of the Royal Astronomical Society of the United Kingdom, the first female president of the Institute of Physics for the UK and Ireland, and the first female president of the Royal Society of Edinburgh. And she has received many awards, including the Breakthrough Prize in 2018. Today, she's going to talk to us about the discovery of pulsars. So Jocelyn, thank you very much for coming, and you may start.
Thank you very much, Paola, and thank you for the opportunity to be with you. I'm afraid I do not speak many foreign languages. I am going to have to give this talk in English. I will try and remember to talk slowly, but I may not always remember.
Okay,
So
thank you.
what happens now? Yes, okay. I'm going to say a little bit about my background and then tell you the story of the discovery of pulsars. If I have time, I will also tell you some stories of where pulsars were nearly discovered, but were not actually discovered. So I started life in Ireland, in the north of Ireland, and I started by failing an important exam at age 11. I subsequently learned they had a higher pass mark for girls than for boys, because too many girls were passing this exam. I started doing science in the senior school next term, and we did physics that first term, and I came top of the class in spite of having failed an important exam a few months earlier. We did physics that first term, it was good. We did chemistry the next term, yeah. And in the third term, we did biology. Here is a flower. Draw the flower, label the parts, learn the name. Oh, you've done that, right. Here is another flower. Draw this flower, learn the part, label the parts, learn the names, and so on. And I thought that was boring. And all the way through school, physics was my best subject. So I went to university to do physics. First of all, to the University of Glasgow to do a standard physics degree, because I'd already decided I wanted to be a radio astronomer. And after that bachelor's degree, I went to Cambridge to do a PhD. And the photograph on the right shows Cambridge. At that time, it was very full of young men, confident young men, and very, very few women, although these days there are more women. I was a bit scared when I got to Cambridge. Everybody, all the young men, seemed very clever, very confident. And I was thinking, oh, yeah, they've made a mistake admitting me. They shouldn't have. I'm not clever enough. They will find out their mistake. They will throw me out. But until they throw me out, I will work my very hardest so that when they throw me out, I will not feel guilty. I will know I've done my best. So I was working very hard. This shows the bits of Britain that I had lived in up till then. I started there, I went to school there, I went to university there, and then I find myself down here, the flat, rich part of England. And this part of England thinks people up here are terrible, barbaric, wicked, heathens. It's this part of England that's civilized. So I really felt out of it in many, many ways. As I started my PhD in radio astronomy, I'm given some tools. These are my tools. I still have them. And these are not delicate electronics tools. These are heavy duty wire working tools because I'm going to be doing heavy work. This is near the end of the second year. I have been putting plugs and sockets on these cables, and now we are testing that the connections are good. It is winter time in Britain, and this little hut is all the shelter that I have. The telescope was designed to work at 81.5 megahertz. There were over 2,000 antennae, over 1,000 wooden posts, almost 200 kilometers of wire and cable. And it took several of us 2 years to build that radio telescope. This is a finished article. What you can see mainly are the wooden posts. The wooden posts are to keep the bare copper wires away from the grass. These are the antennae, and along here. And then the signal comes down these loops of wire, along some more wires, into cables, and back to the receivers in the laboratory. Now, at that time, quasi-stellar radio sources, quasars, were a very big puzzle. When radio astronomy started, the first thing people observed were some very strong radio sources. And when the optical astronomers were asked, what is there there? They'd say, well, it's a bit like a star, but not the kind of star that we're used to. It's a curious kind of star. And so they became known as quasi-stellar radio sources, or quasars for short. And optical astronomers, particularly Martin Schmidt and Jesse Greenstein, had got spectra, optical spectra, of objects that seemed to be at the right position. But they could not make sense of the spectra until suddenly Martin thought, is it a hydrogen spectrum with a very big redshift? Very big. So big, he couldn't believe it. But he went along to Jesse's office. Jesse has the spectrum of another one, and he thinks it's probably made of tellurium. And he's trying to write a paper explaining why this object is rich in tellurium. And Martin comes into the office and says, Jessie, could it be a hydrogen spectrum with a large, very large redshift? And Jessie says, ah, yes, that's it. But it was a very, very large redshift. That was disturbing. It was so big. Because the large redshift implies the things are very distant, but they're also very bright. If they're very distant, you would expect them to be faint. So they seem to have things that were very distant and very bright. And they became known as quasars, which is short for quasi-stellar radio sources. Now, these objects were very, very compact. They're not spread out, they're compact. And when you have a compact object, like a quasar and a radio telescope, the radio signal comes to the radio telescope through the solar wind. And the solar wind is not smooth, is not uniform. It has high density, high, low, high, low. And this acts for radio waves like a diffraction screen that is moving past. And as it moves past, you get a signal like this that rapidly varies. Because some of the time you see the quasar signal through one of these clouds in the solar wind, and sometimes you see it through a gap, and then you see it through the next cloud. And so the signal goes up and down very fast. This is called scintillation, and it's called interplanetary scintillation because this is the solar wind between the planets. Now, back at that time, the University of Cambridge did have one computer, only one. It was before transistors. It was made with the vacuum tubes that you plugged in. And it took up a whole room and had memory less than your laptop. So the whole university had one computer with memory less than your laptop. And very few people could use it, and we did not have time on it. So my data came out in hard copy on paper charts. And there was a lot of paper chart, 30 meters every day. One sky scan took 4 days, 120 meters. And after 6 months, I had 5 kilometers of this paper. And I had to analyze it by hand because we had no access to a computer. So we kept scanning the sky, 4 days to make one scan, then start again, 4 days to make another scan, start again, 4 days, and so on. It was a very successful program. We started with about 20 quasars known, and by the time I'd finished, we had multiplied that by 10. We had 200 quasars. So as a project, it was very successful. Oops, sorry. But I was being very thorough because I thought they were going to throw me out. And there was one little bit, about 5 millimeters on this meters of chart paper, 5 millimeters that did not make sense, 5 millimeters that I could not understand. And it kept sidereal time. It came around 23 hours, 56 minutes later. So it's not something that human beings are doing unless they are astronomers, because the sky and astronomers are the only ones that keep this 23-hour, 56-minute day. Well, maybe I had wired the telescope up wrong. Maybe the receiver was misbehaving. So we got a colleague who had a separate radio telescope and a separate receiver, and they looked very confidentially, they looked to see if they could see it, and they did. So it's not interference because it keeps sidereal time. It's not faulty equipment because it's been seen by a separate set of equipment. It must be something out there. I nicknamed it Little Green Men. This was just a nickname. It was not a serious name, but you had to call it something. And we decided we could check this because if they are little green men, they live on a planet which goes round their star. And as it goes round their star, when it's coming towards us, the pulses are closer together, and when it's moving away, they're further apart. Doppler effect. Well, we looked for this, and we didn't very obviously find anything like that. We did establish that the Earth went round the sun. So we've proven again that the Earth goes round the sun, but we see no other Doppler shift. And then, thank goodness, I found a second and a third and a fourth. Oh, sorry, I've gone very... Right. Okay. So finding some more was a great relief. We managed to get a dispersion measurement as well, putting it about 200 light years away. But really, confirmation with another telescope and finding some more were the best bits. So I ended up finding 4 of these. We wrote up the first one first to get published, and then the other 3 came in a later paper. And Tony, my supervisor, just before the first one appeared in the paper, he gave a colloquium in Cambridge, and he gave it a very exciting title, Discovery of a New Kind of Object. At that stage, we had 2 ideas about what these things might be. Excuse me, I just need to reach for my prop. I don't know if this is going to work. Yeah, right. Can you see a little thing on your screens?
Yes.
Yes.
Good, right. There's 2 possibilities for this object. It could be vibrating or it could be spinning. And the crucial test is, how does it behave as it slows? If it is spinning, go up, yeah, try again. This is not the best laboratory bench. No, let's try the rocking. Did it quite nicely. If you have something vibrating, as it slows, sorry, as it ages, it gets faster. So let's see if we can see this. I could perhaps provide you with a better background. That's better. You see the way as it slows, it gets faster, it stops.
Yes.
Its amplitude drops, but it
Yes.
gets faster. Whereas if it's something that's spinning, it slows before it stops. So with time, if it gets faster, it's vibrating. If it gets slower, it's spinning. And some other astronomers observing that first pulsar saw that as it aged, it got slower. So it's a spinning object, not a vibrating object. So that was an important observation. It didn't take place till about 6 months later. And until then, we had these 2 ideas, something spinning or something vibrating. And Tony's idea that he presented in that first colloquium was that it was a star like a white dwarf, probably, most compact known kind of star, vibrating and launching shocks into its atmosphere, which somehow give radio pulses. So Tony gave this colloquium in Cambridge, gave it a very titillating title, and everybody came. And I remember Fred Hoyle sat in the front row. And Tony went through what we'd done and what we knew about these things and put forward his theory that it was a vibrating white dwarf. Fred Hoyle, sitting in the front row, was the first person to speak. And he said, I don't think it's a white dwarf. I think it's a neutron star. And Fred Hoyle was right. Only 40 minutes earlier had he first heard of these things. And in 40 minutes, he's absorbed the information and come up with the better explanation. He had an amazing brain, that man. But Tony still thought it was something oscillating. And it wasn't till much later we could get the period derivative and could see that it was in fact slowing, that we knew it had to be a spinning object. The paper announcing the discovery was published in Nature, and quite a lot of the newspapers took notice. And that was a particularly difficult bit for me. Usually the two of us, Tony Hewish and I, would be interviewed together by a journalist. And the journalist would ask Tony about the astrophysical significance of this discovery. And Tony would give it. And then they turned to me, the young woman, for what they called the human interest. How many boyfriends did I have? What were my bust, waist, and hip measurements? Would I describe my hair as brunette or blonde? No other colors were allowed. It was disgusting. It really was. I was simply there as a sex object, not a scientist. And Tony did nothing to correct the impression either. But one of the science correspondents was really useful. He worked for a newspaper we call the Daily Telegraph. It's one of the intelligent newspapers, but very conservative. However, they had a good science correspondent called Anthony Michaelis. And he asked what we were going to call these objects. And we had given some thought to this. There were two possible names, a pulsating radio source or a pulsed radio source. We opted for pulsating because pulsed might mean somebody making the pulses, little green men. So we said pulsating radio source. He said, no, too long. What about pulsar? Because we already had quasar. And so pulsars they became, named by this man, Anthony Michaelis. One of the advantages of having been involved in the discovery is that every so often, at a conference maybe, somebody comes to me and says, you know, I nearly discovered pulsars, and tells me their story. And they're quite interesting stories. They tell us a lot about the way science works. So here's a summary of those stories. The first one is about 1957. We're in the United States at the McDonald Observatory, and it's a night when the telescope is open for the public. And the technician has set the telescope on Minkowski's star, the curious star in the center of the Crab Nebula. The story is told by Elliot Moore, who was a summer student working at the observatory. And people stepped up to the telescope and said, "Oh, wonderful, gee whiz, wow," whatever they said in 1957. And a young woman steps up to the telescope and says, "That star is flashing." And the night assistant starts to explain about scintillation and the Earth's atmosphere and twinkling of stars. That star's flashing. She goes on to say, this is 1957. She has a job as an airplane pilot. Her job is to fly airplanes from the manufacturer, from the factory, to the customer. She flies at night. There's not a lot to do in the cockpit at night. She knows the constellations and she knows that the stars scintillate or twinkle. That star's flashing. Now, the interesting thing about this is the Crab Nebula star does flash. It flashes at 30 hertz, 30 flashes per second, which is close to the limit that human beings can see. But we know that young women in particular can see, or some young women can see 30 hertz, because in Canada, the main power supply used to be at 30 hertz. And some women were driven crazy because the lights, the television, everything is flashing 30 times a second and they can see it. So we know that some young women can see 30 hertz. We suspect she saw the Crab pulsar flashing, but nobody followed up. This gentleman is Charles Schisler, or maybe he was Charles Schisler. I'm not sure if he's still alive. Suddenly in 2007, the Australians, who have an online catalogue of pulsars, get a very excited message from him. He worked for the US military. He was stationed in Alaska, looking out for missiles coming in from the Soviet Union. When it was quiet, he was allowed to play around with the equipment. And he used the receiving equipment and looked around the sky. And he said he discovered 14 pulsing signals, one of which turns out to be in the Crab Nebula. When he was a student at college, he had done an astronomy course. He knew about right ascension and declination, and he's written down on a little piece of paper the right ascension and declination of the pulsing sources he's found. Illegally, he takes that bit of paper with him when he leaves the military. And now he has just discovered the online pulsar catalogue that the Australians keep. And in it are several of his pulsing objects, as accurately as he can tell, including the Crab Nebula. He couldn't publish. He was forbidden by Air Force rules, but he had kept this little bit of paper. And now that he has discovered the online pulsar catalogue, he's emailing the Australian radio astronomers, telling them how he observed these sources way back in the 1980s when he was working for the American military. So 10 or 11 of them have been identified, including that's the Crab Nebula. And even though he's 81 years old, he's very excited by all this. And he has quite a lot of correspondence with the Australians and comes to a meeting and tells us all about it. Another example of pulsars nearly discovered involves Sue Simpkin, who at that stage was working in ultraviolet astronomy. Sue Simpkin was brought up in Canada. Sue Simpkin brought up in Canada at the time when their power supply was at 30 hertz. And she was one of the women who could see the flashing. She's now working in ultraviolet astronomy, and Low Vulture has asked her to take a spectrum of that curious star in the center of the Crab Nebula. She takes an ultraviolet spectrum. She says the star is dull, but she can see flickering or waves or something going out from the star. Low doesn't believe her until the discovery of pulsars is announced. And then he says, yeah, maybe you did see it. But she didn't feel convinced enough that what she was seeing was sensible. For the final example, I am not going to name the people involved. They were very embarrassed at not having noticed pulsars. They are radio astronomers. They're doing a map of the whole sky at 408 megahertz using the world's largest telescope. So they get 5 nights on this telescope and 3 days on that telescope. And they've nearly finished the all sky survey. They've just got 1 or 2 little patches to fill in. And they're doing that. It's still the era when there are pen recorders, there are not computers. And one of the pen recorders misbehaves a bit. 3 o'clock one morning, that pen recorder starts going weep, 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 weep. And the observer says, oh, damnation, and thumps it. Because that's the way you make a pen recorder not be sticky. And sure, the pen recorder stops doing this and goes back to its normal pattern. And the observer says, good, puts on his coat and goes home to bed. And he did not make any entry in the logbook. They had actually been at that point observing, we now know, the pulsar 0329 plus 54, which is a period of about this. But he made no entry in the logbook, so it's only his memory hearsay. And actually what is also sad is they've done this all sky survey, and following the discovery of pulsars and the announcement of the discovery, they didn't go back through their data to see if they had found any pulsars, because that pulsar that they observed was not one of the ones that we first found. It came along later. So use your logbook, folks. Keep a note of anything peculiar that happens. You might have made a major discovery and you need the documentation. I want to finish by paying tribute to Franco Pacini, an Italian astrophysicist. There'd been considerable puzzle before pulsars were discovered as to why the Crab Nebula was still shining. We knew that there had been a supernova. It's been reported. It was about 200 years, 300 years previously. And the nebula initially was the debris from the exploding star. But with time, that debris should have got fainter and fainter and fainter. And yet it's still bright. Why was this nebula staying bright? And Franco Pacini came up with the idea that there might be a neutron star, wow, in the middle of the Crab Nebula, that it had a large magnetic field, which was inclined to the spin axis. This would produce magnetic dipole radiation at the rotation period, and if the nebula was dense enough, that radiation would not escape. It would get stuck in the nebula and keep the nebula shining. He was absolutely right. This was before pulsars were discovered, and he's hit the explanation of why the Crab Nebula keeps shining. He was a brilliant astrophysicist. I'm on my last slide or two. Factors that led to the discovery, when and where it happened. First of all, I had my own telescope and receivers, and I made sure I understood how it behaved. I knew about its anomalies. As a research student, I had time and space to do that. And remember, I'm also suffering from imposter syndrome. I think they're going to throw me out, and I'm working my very hardest until they throw me out. So I'm being very thorough. I am following up anomalies. But this was one of the first observations made with a short time constant, a short exposure time. Up till then, longer integration periods were needed, and those would have averaged the pulses. And incidentally, we weren't aware of any other observers likely to make the same discovery. So we could be careful, take care, be thorough before we rush to make an announcement. And being in the University of Cambridge, we had a good address. If you make a crazy discovery, please have a good address. If you make a crazy discovery from a place that does not have a good reputation, you've had it. These days, it's very fashionable to set objectives or targets for programs. This wasn't one of them, of course. If we had been able to computerize the search, if we'd had access to a computer, would we have programmed the computer to look for pulsars, which were nothing to do with our program and we didn't know existed? Possibly not. If it had been computerized, we might have missed it. And those low frequencies and high time resolution have been an unfashionable combination, but more now we're seeing it being exploited. So thank you for your interest. Thank you for your attention. And I hope I haven't kept you too long.
Thank you very much. It was fantastic to hear this story from you. I think it's a privilege to all of us. And there are already questions in the chat. So the first one that I can see is from Eduarda. Would you like to make your question in the microphone? And also please raise hands or leave the comments in the chat if you would like to make a question. So while I talk to Eduarda, maybe we can move on. So we have a question from Caroline.
Hi, I think that my question, thanks for the fantastic talk, it was amazing. Very, very nice to hear you. My question, I have two questions, actually three, if I may. So the first one is, what was the time scale for the quasars, for the pulsars observation, in order to distinguish between the, the slowing down or the speeding up of the effect? The second question is, how did you go through that kilometric data? How was the analysis? And I mean, if you, in the end, I don't know, maybe comment a bit on your recent works.
Right. Okay, that's about 3 questions.
Sorry.
We were not at that stage able to measure the slowing down or speeding up. We just did not have a long enough observation. That came later. So at the time, we weren't able to have that information. And I've forgotten what else you asked, sorry.
How did you analyze that kilometric data, the kilometric paper?
Well, I had a nice wide table and I had the roll of paper at one end and I moved the paper gradually across and more and more and more till I'd finished the roll of paper. And as I went across, I was noting the quasars, the right ascension, declination of things that probably were quasars. And because we repeatedly surveyed the same patch of sky, if it was interference, it probably would not occur at the same bit of sky, whereas a quasar would. Yeah.
Thank you.
So the question from Eduarda, I will try to translate it. It's the following. Have you observed this object disaccelerating clearly, even being an astronomical object? Because our lifetime is so small if compared to the universe time. So how was this process, and how long did you wait to see this change?
Right. The periods typically are good to 6 or 8 decimal places. So the change in period is very, very small. And the way you measure it, we couldn't do it, but the way other people have measured it is you accumulate the information you have on the period. So, you know, if you observe it in one day, you can say the period is 1.33 seconds. If you can observe it 3 or 4 days, you add more decimal places, and so on. So the more you observed it, you were able to add more decimal places. And then you find that the last decimal place is changing. It's slowing. So you can measure the slowdown rate as well.
Okay, thank you. Next question from Katarina.
Hello, Professor. Thank you so much for this talk, and also for being such an example and an inspiration for us young female astronomers. I'm not sure if you got it, but the presentation before yours by Larissa, she presented her work that she was studying your discovery and serendipity with some other concepts. But I mean, just to say that you are really someone that is a role model for us. And then I wanted to ask if you have any advices for young women that are starting the career in astrophysics or cosmology or gravitation, if you have any piece of advice for us. Thank you very much.
I think astrophysics is a very, very exciting area to be working in right now. Lots happening. New things like gravitational radiation opening up, you know, lots of new developments. So you probably have a problem of choice. What will I do? Which will I do? But whatever you do, I think, particularly for women, it's important that you do good quality work. There are still people around who think women cannot be scientists. And so it's really important for all of us to do good quality work and present it well. Present it clearly, talk about it clearly, and that will encourage other women, especially younger ones, coming along behind you. It's still not a completely fair world, I think, at least in this country. Maybe where you are, it is more fair. Maybe it's very fair.
Okay, thank you. So
Paola,
Katarina.
maybe we can stop sharing
yes.
so we can see everybody.
Yes, it's okay. Can you stop sharing for me?
Indeed, sorry about that. Yes, and I have been probably giving you strain of the brain. Yeah.
Thank you. So next question from Laura.
Hi. First of all, I feel like a teenager talking to a pop star. The reason that I do astrophysics is literally because of you, because I went to Cambridge and I saw everything about your history, and that's the reason why I made the decision to pursue this career. So I'm only here because of you. I feel like crying, I'm sorry. What do you think was your biggest challenge, and how did you face it, and how did you go towards it, and how would you recommend us to deal with the challenges, especially as women in a such male-dominated world?
Yes. It's my answer to that depends on the social conditions that you are living and working in. For me, the most difficult bit was managing having a marriage and a child and a career. The combination was very difficult to manage. the marriage ultimately broke up. The child became a physics professor. So I got that bit okay. So yeah, getting good jobs for two people, husband and wife or partners in the same place is difficult. And small children, well, inevitably they get sick. They get sent home from school and somebody needs to go home to take care of the child. And when I was a young woman, very few married women work. The husband would never go home from work to look after a small child who was sick. It was always the mother. I don't know enough about Brazil to know what the situation is in your country, but it is difficult to manage marriage and having a family as well as a career, which is very sad because actually we need the marriage and the family to keep us sane while we have this crazy career.
Thank you.
Okay, next question from Alta Stella.
Hi, Jocelyn. Thank you very much for your speech. It's emotional to listen to a person who lived so much and to share with us with this emotion too about all the time, the effort you had, you and the people from that epoch. Very nice. Thank you very much. I have two questions. One of them is about, I'm thinking about a child. I coordinate a planetarium in Rio Grande do Norte, Brazil, northeast of Brazil. And we've been in touch with a child. Sometimes she comes there. And the question is if you have any advice for parents who have children with supposedly high ability or high focus on astronomy, what kind of advice maybe you could give to the parents too? And the second is, I think I've read that your parent who worked in a planetarium, maybe he designed something in a planetarium close to your house. And I'd like to ask if you have any memory you would like to share with us about the planetarium in your life, maybe stimulating your interest for astronomy, if you have something you would like to share. Okay, I don't know if it's the English is okay.
Yeah, indeed. Much better than my languages. Thank you. The planetarium. My father was an architect, and about 40 kilometers from my house, there was an observatory, Armagh Observatory in Northern Ireland. And they decided to build a planetarium. And my father was the architect for that planetarium. So it was a planetarium beside the observatory. I went with him sometimes to the planetarium when it was being built. And indeed, having found the first pulsar, no, having found two pulsars, I then, in the next holiday, went to the planetarium that was being built. A rather dramatic Englishman called Patrick Moore was the first director, and he had just installed the projector, and there were stars on the planetarium roof. And Patrick was talking very enthusiastically, very fast, with lots of hand waving, because he always did, about this sky that he had projected. And I was working out, where is this thing that I have found? And I could see it was in the Milky Way in a very crowded field. So that's my main planetarium experience. For children with high ability, certainly for English-speaking ones, there are now things you can do online, science projects. There are many science projects in Britain that need the public to make observations. How many birds can you see in your garden today? Please go and survey trees near where you live. Measure their girth and how tall they are, and enter the data on a web base. So we have, these are called citizen science projects. And we now in Britain have a lot of citizen science projects. And they're good, maybe not for tiny children, but for children sort of about 7 or 8 onwards could do them. And some do, along with their schoolwork.
Thank you.
Next question, Isabelle Lacerda. Isabelle, would you like to talk on the microphone, or may I read your question? So while Isabelle thinks about it, Manuel, please go ahead.
Yeah. So, Jocelyn, I am a professor from Aeronautics Institute of Technology near São Paulo. And in fact, I have the pleasure to be with you, but of course, you are not going to remember because we were together with even Jaziel, that is now a professor organizing all these things, when you were here in Brazil, in Rio de Janeiro. Yeah. We take a picture with you and so on. But I have one question of science and another one that maybe I am not aware, and maybe here in this meeting that I was not aware of humans maybe already exist. So my first question about science is, do you believe that could have dark matter inside of pulsars? Or at least what is your opinion? Okay, because no one knows, but do you believe? And the second question is, exist nowadays specific programs or collaborations in the big telescopes, collaborations in Chile, for instance, that are really to women, in the sense that exist some positions for women to do their research specifically, like exists this STEM movement, no, or no? And is it possible to really develop that with these big collaborations? So that these two questions. Sorry if I talk too much.
Thank you. I believe that Brazil does rather better than Britain for having women certainly in astronomy. The International Astronomical Union keeps data on its membership divided into men and women, only 2 categories, but at least divided into 2. And South American countries and South European countries have higher proportions of women astronomers than do North America and North Europe. So congratulations. I think that's good. And maybe you can show the Northern folk what to do. The inside of a pulsar, or the inside of a neutron star, this is still not fully agreed. There's quite a lot of work going on this still. My office mate is one of the people working on it. I don't claim to understand it all in great detail, but I know the physics is very extreme. It's quite difficult physics inside a neutron star. I think it's very far from settled. I think a lot more work is needed before we finally agree. And of course, immediately after the supernova, conditions inside may have been one kind of thing. And then as it cooled and time elapsed, maybe it settled into something else. But there's a lot of very fundamental physics going on inside neutron stars, for sure. They're very important for physics.
Thank you very much. Thank you.
Thank you.
The next question is from Isabelle, is the following. How did you deal with the imposter syndrome, and what advices can you give to young students who are struggling with the syndrome?
Yeah, I think always try and do your best work. Do the very best you can. I had that as a kind of defense mechanism, so that I would feel after they threw me out that I had not wasted the opportunity. But I think also it's good recipe for every time, everywhere. Do really good work. Be careful, be thorough, and learn to present it well. Because if you do good work but cannot explain it, present it, that's not so good. So also learn how to present your work.
Thank you. And now there is another question from Rafaela Expone.
Hi, this is actually the Institute of Cosmology and Gravitation, and we are listening to the seminar live. So I recall in another fantastic talk of yours that you mentioned that upon entering the classroom during your university time, you were just a few female students, and the male students would make huge noise to greet the female students arriving. So I was just wondering if you could please tell again this episode, and also how you made it through, what you thought every time, what you told yourself to encourage yourself, because at the time, of course, you didn't know it was going to go well. I mean, you don't have the knowledge you have now. So what would you tell yourself when it was happening without knowing that your work would win the Nobel Prize one day?
Thank you. Yes, this was when I was an undergraduate doing my first degree in Glasgow in Scotland. And it was the tradition then that when a woman entered the lecture theatre, all the men would whistle and stamp and bang the desk and catcall and make as much embarrassing noise as they could. And also if you asked a question in class or answered a question in class, that would happen again. I was lucky in that I knew what I wanted to do. I knew I wanted to be a radio astronomer, and I knew I had to get a physics degree in order to do research in radio astronomy. So I really had to do that degree. The tendency, of course, when you're faced with that is that you blush, you go red. I learned to control that blushing so that I did not go red. I could walk into the room with my nose in the air, take a seat and pretend I hadn't heard. It was decibels of noise, but I could pretend I was ignoring it. And that really, I think, was the only way to survive. Because I worked quite hard, I was never top of the class, but I was usually up in the top 5 or 10 of the class. I think if I had been much lower down the class, I might have given up and gone and done something else. I don't know if that still happens in Glasgow. It was very much a local tradition. It didn't happen in the south of England, for instance. It was just in Scotland at that time. And it was in areas where the women were in a very small minority, engineering, physics, for instance, but not in the art subjects where there were lots of women and not so many men.
Thank you
Thank
very
you very
much. Are there other questions?
Acho que a gente já pode fechar, Paola.
Yeah, so if not, I would like to thank Jocelyn. Thank you very much for coming here. It was a really interesting perspective to see this discovery told from you, and also your perspective about the paths as a woman in physics, in astronomy. I think it was a great experience. I think I can say that for all of us. So thank you very much.
Thank you very much. It's been enjoyable for me. All the best.
Can we take a picture?
Oh, can we manage it?
Yes. Please. It will be a treasured memory for all of us.
Who is taking it?
Pessoal, se puder abrir a câmera, todo mundo, para a gente tirar uma fotinha.
I already took some, so I think it's okay. So
Thank you,
you-
Manu.
Thank you.
thank you
very much.
So
Thank you
you.
very much.
So just
Enjoy.
before you going, Jocelyn, I just would like to say that our event, it's a Brazilian event, of course, but also the idea was embraced by Rafaela and Daniela from the ICG in Portsmouth. So they are transmitting your talk there as well, and then they will discuss a little bit about our role as women in the community. So we'll discuss in the Brazilian community, and they also will discuss their roles there also in Portsmouth. So it's super nice, and thank you for your time. That's all.
Thank you very much to all of you. It's been fun being with you. Take care.
Thank you.
Thank you, bye. E lembrando todo mundo que a gente volta às 1h30, tá? E não 2 horas hoje. Temos a apresentação da Stephanie às 1h30. Bom almoço. Thank you so much, Jocelyn.
Thank you.
Lembrando também que a sala vai ficar aberta, gente. Então, quem quiser ficar... Eu acho que outra vez.
Eu não ouvi o Manu.
Acho que já pode parar a gravação, né?